about other roles that I'm playing.
Yes.
Um, yeah. So hi,
All right.
name is Brian Muhia. I am the co-founder of Fahamu and also the CTO of Equiano Institute. So Fahamu is uh, a startup started in November 2022. The vision of the startup is to build learning assistants and um, generally AI assistants, and to make sure that they are actually helpful. And I started with a background in uh, research in AI safety, uh, specifically the subfield of interpretability, where we try and explain how AI systems work. And so the field of interpretability has kind of uh, exploded in popularity in the past few years, since especially since deep learning became a very popular thing. Um, it became very useful to like have the skills to be able to explain how AI systems work. And so um, the uh, the motivation for me was to to be able to explain systems to practitioners, uh, in the sense that when the practitioners have a good way of explaining the systems to other people in their teams, non-technical people, other stakeholders, then as an engineering effort, like they actually have the ability to help more people in that way, right? They're not just building stuff, but they're also being able to explain how the systems are working. It would help with oversight in the sense that when we know how the system works internally, then we can more people can suggest changes, more people can challenge the system's design and uh, verify that everything that is expected should be the way is expected to be. And uh, so that's what the work that I've been doing is mostly centered on, at least on the research side. So uh, that led me to also meet and find that I had a lot of good synergies with other researchers who are working in the same field. So some of my research time is spent on writing papers as well. So the paper that I'm presenting now is the first paper that has come from this program, basically explaining LLM systems using a certain kind of notation, and then exploring the benefits that come from that notation. Like, um, so I'll walk through each of these steps. So,
Yeah. And then, sorry for interruption, Brian. How do you prefer, like, if someone has a question, we wait till the end, or they could just interrupt and ask you?
so you can interrupt and ask.
Okay, good.
Yeah. So I think there are few enough people that it'll benefit more from something more interactive. So that's okay. So right. So I'll say described kind of at high level what the project is. So we have systems that are uh, interacting with a large language model, right? So think of um, you have a web application, or and in that web application you let someone ask questions, and some of those questions are sent to an LLM, and then they use data in the background. So you have a database or a bunch of documents that you want to search against, or you want the LLM to answer against. So the product that I've been working on for the past year or so, Digest, is like that. So what we do is have we let people upload documents. Uh, Optionally, we let them connect databases, and then we have all of these retrieval methods, right? So when someone asks a question, the system searches the background knowledge base, the documents, files, or the database, and then the relevant content is sent to an LLM to summarize, to answer the question, or to generate more questions based on what they want. So a related example, in Microsoft, you have Bing or Bing Chat. It's the same kind of process, right? So for Bing, it's the web. For Digest, it's like a local database or a set of documents. So this process, and like the way we go through this is by decomposing the question that someone asks. We do this in many different ways, but the primary method is like when you have a question, you get you decompose the question into sub questions, and then you aggregate them. You get the answers of the sub questions, and you aggregate them into an overall answer. And this is called factored cognition. This was pioneered by an organization called OT. If you want to look it up, you can check this URL. There's a book with a bunch of concrete examples that I will also go through at some point in the talk. So yeah, so this is factor cognition, and then I introduce a kind of notation for describing the data flow in the system. So whenever you ask a question, the sentence you type, whatever the question is you type, gets sent to a search engine, and then the contents of that search engine are sent to an LLM. And then when those responses are sent to you, that whole process creates a kind of graph. It's a causal graph. So that's the process we're describing, and generally, like I described, the components of this are the question that the user asked, the final answer that you get from the system, then the background data source, so the list of documents, the database, and so on, the context of the model, which is when you basically look at the data source, you will find relevant content, and that content is what gets entered into the context of the model. This is what the model actually sees based on what was in the data source. And then optionally, sub questions and sub answers, which are generated by sub agents, which we'll discuss. So this, you can imagine, if you imagine like what's happening in the background of a system like this, you have things happening in steps, right? So the user asks the question, the search engine runs, finds paragraphs, and then the paragraphs get sent to the LLM. And optionally, there's sub questions and sub answers. So there's a whole chain of things happening. And this is a causal graph. It's directed in a cyclic. So it's directed towards getting the answer to the user. It's a cyclic in the sense that there are no loops. So we'll discuss what those things mean in the paper. Yeah, so, and this process is described, I claim it's described naturally using these diagrams, causal inference diagrams. So a causal inference diagram is just a graph. If you're familiar with, in Python, the library NetworkX describes graphs pretty easily. So it's the same thing. So we have nodes and edges, and then basically the nodes are connected to each other by edges. The edges have arrows, which denote something that we'll discuss, the directionality of the arrows. Then there are types of nodes. So here we have they're partitioned into three. So we have decision nodes. These blue squares are decision nodes. You can think of them as the model that is responding to the user, or the model that's generating content. And then utility nodes are the diamond here. So the diamond is something like whenever the system answers the question, the user will press upvote or downvote based on whether they like the answer. So that's why I call it a utility node. Utility in reinforcement learning is the thing that is being searched for by an RL agent. It's searching for reward So this is, we actually want to model this process in the system. Then finally, we have chance nodes. Chance nodes are the thing that is kind of outside of this. It may be outside of the scope of the model. In this case, we have the user's question, or I. Here we call it intent. And then C is the context, what the model actually gets to see based on the contents of the data source. So here we had data source and context. Right? Context is the results. It's like the search results after filtering for relevance. Yeah. So these are the three things. Actually, these are actually the three components of at least one of any one of these diagrams. We have context, the user's intent, the decision node, which is the model which is answering the question, and then the output, what the model responds with. So this this diagram describes the simplest case of this kind of interaction. So if you've used BARD, if you've used Bing Chat, you can imagine something like this happening. Right? Whenever someone types a question in the search bar or in the chat box, the system starts a search process. This is the directionality of the arrow. Like the data from the user is going to the search process to find context, and then the data from the user is also going to the model, right, to prompt it to do something. And then the context also goes to the model, because that's what we want. We want the model to be answering questions about the context. And then the model outputs its answer, and then the user gives their vote, right, up, down, deciding whether they liked the answer or not. So this is the first case. If you have any questions, you can ask here, and then we can move on to the next steps. So
I didn't get the that context part. Like, if you could just give an example of what would be like a context in a maybe with a basic question that the intent that the user is asking, and then what would be a context that will be generated.
Sure. So I'm going to show the interface that I've been building, and then we can use that as a basic level of this. So I'll just transfer the share to the interface quickly, and then I'll come back to the paper. So here I have I guess a database of PDF documents. This is one file that's been found to answer the question. So this is the question that I asked. What are the US and EU doing to create a legal system for AI? Then we have context from the documents. So you can imagine, so if I scroll up here, we have 27 documents, right? For this one answer, for this question, one document was found to be representative of the answer, right? So this is the context, right? All these are paragraphs that are in the database. Out of all of those thousands of paragraphs, only these paragraphs have been determined to be ones which are answering the question. So you can think of the data source as the database of every other paragraph that's been extracted from the files that have been uploaded to the system. And then the context is what is determined to be relevant by the filtering process, right? Then this is the answer that the model generated, the final answer. There's a bit here that is going to be relevant for the next steps, which is these sets of questions and answers. But I will go back to the paper first, and then we'll walk through those at that point. So does that make sense from this point?
Yes, it does. Thank you for that.
Okay. So right. So this is the basic system. Yeah. So this is the important thing here is to visually look at the diagram and see that there's an arrow to each relevant component from the intent node, and then to see how to fix it, or to see basically what might be wrong. Basically, we're trying to, with this kind of work, we're trying to develop a practice for verifying the system's data flow outside the code, because the code is complex to read, and then there might be all sorts of things. You might be like incentivized to fix the code immediately, but what we want to do is have descriptions of the system as it is, or different systems as it could be, and then decide based just on the diagrams whether or not we want to implement it. Right. So, and the way you do it is just look at that. We look at the arrows. So now, the thing that's happening here is there's a trust problem, because we know just through observation in the past several years, or at least in the past year, that you can't always trust, even if we know that the model knows what it is being asked for. You can't always trust its output, right? Like even Bing Chat will hallucinate even if it's gotten stuff from the internet, right? Even if it's gotten stuff that's ostensibly relevant for the question, it might still say things that are not correct. So the way one way we can deal with this is improving the model, or adding another copy of the model, in the sense that we make multiple calls to the model to do something. So this is what we do in multi-agent scenarios. So we have one request, the user's intent. Again, it's the first thing that happens is to search for context, and then the intent goes to the first model to do something. Maybe it's been asked, the first model has been asked to generate one extra question, or this is the model that's been asked to answer the question. And then the second model has been asked to verify that the answer from the first model is correct, right? So and this is basically the case, right? If you want to improve the robustness, one of the ways to do it is to add a few steps. They increase the latency. Like this is, you can look at this arrow, you're saying this is one time step, and then another time step, and then another time step, and then finally the answer comes to the user. So it's increasing the amount of time it will take for the answer to come back to the user, but it's adding a step where the model's answer can be verified by another system. So this is okay. Although the challenge is we are not sending the user's intent to all the decision nodes, right? So let's say if M2 was asked to verify that M1's output is correct, right? It would only know how to do that based on the context, right? It wouldn't know what to do based on the user's intent, because it does not know what the user actually asked for originally, right? So this missing arrow is what we want to basically, we want to say that this is a missing step, right? And that this diagram is not complete until we add an arrow from I to M2, right? And this is what that looks like. So this is without the arrow, this is with the arrow, right? Here we say, we can inspect it and say, just by looking at the diagram, and say, the step is find the paragraphs that are relevant. M1 has the instruction and it knows what the user asked for originally. M2 has its instructions, and it has basically what to do with M1's output, right? And it has context. It knows what the database contents are, so it knows the subject of the request at least, and then it knows what the user originally asked for. So its decision includes basically considers the user's question to be relevant to its decision. Basically, the whole system now, at least we say at each step, the the user's intent is satisfied, or it's not necessarily satisfied, it is consistent with the user's intent, because it has at least the context is contains the user's question for every model that's in the process. And that's so this argument that I'm making, where we take just by visually inspecting the diagram and seeing that there's a missing link between I and any of the M models, we want to add that arrow and therefore complete the graph, make it correct in that way. So this is the basic argument, the basic thought process throughout the whole paper. And then throughout, we just describe all of the things that might be going on. So for example, we might say that this is fixed, but the challenge is M1 and M2 now have a direct link to each other, which means that if M1 hallucinates, right, as they're likely to do, and M2 is not prompted to be a verifier, for example, let's say M1 was prompted to generate one extra question or something, and then M2 was supposed to answer it, and then finally use that to answer the question finally. If M1 hallucinated and generated a question that did not represent the context or the user's question, let's say it wasn't trained very well, or basically any other scenario where it would just not be able to know what's going on. Like for example, in a search engine, there's lots of things on the internet and lots of untrustworthy content. So if someone's question matches somehow with some website somewhere which contains misinformation, for example, like it's like a keyword search will find that website, even though the direct contents of that website aren't necessarily trustworthy. So if C being a chance node, like it can basically, it's like a probability thing. Like it may represent what the model is trained to do, or it may not represent it. So if it doesn't, then M1 hallucinates, and then M2 hallucinates even more because it got that, and either it wasn't prompted or it's not designed to do that. It's not designed to be a verifier, for example. If it's not that, then the system overall becomes misleading, right? So like the system can amplify the misinformation that's already out there in that case. So this is a risk factor. There are very few, I'm not really sure whether there are actually any known ways to like overcome this, unless like it's adding enough steps that like rank outputs in a better way, or force certain kinds of consistencies and things like that. So this is so this is kind of like an easy way to like point out a problem like that and describe what it would entail, at least when you actually have a system that's visible. So this is one step where we've instantiated one more model to do something extra to make the response robust, and then we described the value of having the intent being present in all steps. But we've also described a failure mode that comes from one model's output being piped to the next one. So another case we can describe is where you have you want to include more models, but you want to save on time, the user's time at least. So you describe parallel steps. So I can describe what the parallel steps look like, at least here. The idea is, if you look at this diagram, you'll see a path from I to C to M1 to O, right? And then there's another path from I to C to M2 to O. So if you think of those steps, if you just look at those steps visually and think of the arrow as time flowing, then you can see that data flowing to M1 and M2 at the same time, right? So that's what I mean by parallel agents, where two models are getting the output from the same system. At least they're getting the input from the same system at the same time. Now the challenge, at least with this diagram, is that both of these models are now outputting their own responses to the user, which feels weird because like you want one model to answer the question and then another model maybe to do the verification. So that can make the interface look a little unusual, where like looking at two model outputs. It might help if you want to compare the output from model A and model B and like judge which one is better. That could be one way to like make to save that situation. But if both of them are wrong, then it breaks down completely, right? Because both of them are equally likely to hallucinate based on whatever it is that was found by the search engine, right? So because of that, we decide to pipe both of these models' outputs to a third model that looks like this, right? So we can again verify that it's parallel, at least that there's a parallel step, even if the whole thing it looks like it's sequential, right? So we can verify it just by looking at the diagram. So we see a path from I to C. So I see M1, M3, O. Then I see M2, M3, O. So the path from I see M1, M3, and I see M2 to M3, those are parallel steps, right? This is something that's happening all at the same time. It's M1 to M1 to M3. So sorry, from C M1 to M3, and then from C M2 to M3. These are the two things that are happening at the same time. The outputs get piped into M3, which perhaps maybe has been prompted to be a verifier, or it's been prompted to take the answers that came from M1 and M2 and summarize them to the output that now goes to the user. So this is a way to get more done than in this step. Like you get at least twice as much exploration in the same amount of time, because it's basically taking one parallel step. So this can gather context differently, or it can be prompted to ask two different aspects of a problem and come up with a solution, and then this third one aggregates those two solutions into one answer that the user can verify themselves. So that's this is like one of the three agent cases. So we say either of these models can hallucinate, but there's a final model which has been designated as one which is either going to be the verifier, or it's going to be the one which is going to summarize the outputs. So like you'll notice all of these ways are ways of coordinating multiple models to do one thing for a user. Just one thing. It doesn't have to be like a long continuous process. It's just like answering a question based on a database, and just finding ways to like collect and aggregate all of this information for the user in such a way that they can verify it and then decide whether the overall process worked for them. So the idea would be like if the user can see all of these steps, right? Like in the interface I've just shown, you don't just see the final answer. You see the context, and you see the sub agents outputs. Right? You see what they actually wrote, that made a contribution to the final answer that you actually get to see. Not all interfaces are like that. Some of them just give you the answer that the model gave you. Some of them can give you references, right? Like they usually have like links and so on. But not all of them give you the exact paragraphs that are used to generate the answer. So this exposing it's kind of like exposing an API but using a different method, right? You could be looking at a JSON object. And in fact, I could even show like the API, like our developer documentation, and how it decomposes into each of these steps, because you can see every single one of these components. nodes in the API. So yeah, so if you want to check for missing steps, right? In this example, I didn't include a missing step. So the path from I to all of the decision nodes is present, and also see like you can see IM1, IM2, and IM3. So the idea is that by seeing this, you can basically have an intuitive idea that the user's question is represented in the model's context. Like it actually saw what the user was originally trying to do. So it should satisfy, at least from the diagram's perspective. Sometimes the models themselves are insufficient. So in practice, the diagram might be correct, but then the model isn't really correct. So in a way, this is like idealizing the whole problem, like taking it away from like the main concrete examples and saying like if we had a system that does this, we at least want all the models involved to see what the user originally asked for in order to have a guarantee that the data flow is correct. Again, you can see the notation here. So I think I'll skip from this to the places or ways in which we can turn this notation into something that basically turns this notation into a kind of a verification program, and then basically we want to turn these intuitive arguments that I'm giving, right? So I'm giving all these arguments about having this node be represented in all these steps. But the challenge is it takes time to visually inspect these diagrams, and then you also have to learn how to like visually inspect them. But then if we have a way of encoding these rules into as a program, then we can basically have a system or process where people will draw diagrams, and then we run a verifier on them on the diagrams notation, right? So we have this is like the actual correct program that generates this graph, right? So if we took all of these nodes, and then we took all of these descriptions, decisions, and then utilities, and so on, and then you run them through a system which has rules that encode these rules that we're saying, like the I node should be represented, the C node should at least should see what the user asked for, because it actually has an effect. That there should be a path from the I node to or any of the decision nodes, and then finally to the output. So all of these rules are simple enough that you can write a program that's basically that you can now use to check all of them. Right? So before we go there, since we've described multiple agent scenarios, are there any questions?
Hi, are you able to hear me?
Yeah, I can hear you, Rogers. We might have lost. Did we lose you, Brian?
I think the video is frozen from my side. This video.
Yeah.
I was going to find out the feedback loop, whether it is out of scope for this. No, in the answer, the output, when the user votes whether
Oh yes.
I'm satisfied with this or not, whether, because here is put context, there's a in the list of the 5 things, there's the database is not represented here, so probably that goes back somewhere.
Oh yeah, because you already need to be like a DAG, so it cannot go like to any of the nodes there. It will fail being an. Oh, that's a good question. I don't know. Let's see. Maybe he just lost. We can need to give him a few minutes.
Yeah.
Hello? I think
Oh, you're back. Okay, good.
yes.
Sorry,
Okay.
you froze a little bit.
Sorry about that.
Even I think what you can do is that maybe you can turn off the video.
Ah,
Then, you know, yeah, that will make it easier.
sure. It will speed things up. Actually.
Rogers has a question. I just can go for it.
Okay. Does anyone have a question as we step through this?
Yeah, so back at the last diagram you showed,
Okay.
looks like you went ahead. You didn't hear you for like maybe a minute or two. So in this diagram, so I was asking about the feedback loop. Was it out of scope? So in the output, when a user says, I'm okay with this question, or I'm not okay with this question, and then maybe the feedback loop goes to either context or database. I'm not sure. Yeah. So the question is whether that was out of scope for this.
It's in scope because so there's a different way of drawing these diagrams, right? So you could draw that diagram where the utility node is connected to every decision node, like O goes to M2, M1, or rather there's like an O1 which goes to the context, and then O2 goes to the M1, and so on until you get the one which goes to M3. Because the user, if the user sees it, right, if they see the context, then they have a chance to give feedback on whether the context is correct, right? If they see M1, they can specifically say that the answer that came from M1 was wrong. And like they can kind of tell as well, like the fact that M1's answer was wrong contributed to M3's answer being wrong, right? And so on. So if the search process is broken, right, like if the paragraphs that the user that the system found for the user's question were wrong, right, like this typically happens, like the ranking is wrong or something, then yeah, the user should be able to like give feedback on that. And basically one of the claims here is that the systems that only give you the model's answer, they're not giving the user a chance to give feedback on every step of the answers generation. So like all systems should expose all parts of their reasoning. And like the claim is that this is, if you want to decompose the reasoning of an LLM system, like one of the APIs or something, then you want the user to at least see each of these steps, and then they'll tell which part of the system, which part of the answer generation process basically went the wrong direction for them. So the feedback loop question is kind of like a longer term thing. Like here you are only talking about in the case when a user is looking at the answer at that point in time. But the general idea can be over time, either one user or many users have given feedback, and then you collect this data, and then someone else verifies it, and then you use it to train the next system, right? Or the next version of the models. So that's the feedback loop that I think you're referring to, right? Because
yeah.
So
yeah, I got it. Could also be a way to maybe audit the system.
Exactly.
Or can have a set of users with those privileges to audit, and others as normal users. But yeah, thanks. I've got it.
Yeah, that's exactly right. It's exposing the reasoning behind the reasoning behind the answers, and then helping auditing. It's exactly correct. Yeah. So this is what I wanted to kind of close with, at least in this section, which is to show that given that you have the notation in this format, so the library, this library called PySeed, this is the standard notation that you use when you're drawing these graphs. So you have the links between the nodes, you have the description of what the node types are. It doesn't describe what the chance nodes are, but these ones are just left as as implicit. Right? Like if you've described what the decision nodes are and the utilities, then the chance nodes are automatically found. Now, in ASP, in answer set programming, we can be more explicit. So as you can see here, we have link where you add just a tuple. We have link CM1. Right? This is describing a link between each of these nodes. So that covers all of this section. We have decision, which says M1 is a decision node. That's one. We have chance. We're being explicit here where PyC does not explicit. We're saying chance represents I and C, right? So in ASP syntax, a semicolon inside one of these params means that you can split this into two lines which say chance. Like these two are equivalent, right? This is just a space saving measure to like just to save on lines. And then utility is right, it's here. So this is the basic scheme. We encode the graph in this way, and then we have these three rules. Let me move this up here so it actually flows better. But the idea is, given the diagram, we want to be able to check certain things. We want to check if there's a path between certain nodes, right? The nodes we want to check a path for are the path from I to C and then I to M1, right? Or I to any of the M models, right? So, and then we want to check that there's a direct link, right? So the thing I'm intuitively arguing for, where like there's a link between I and any of the M models, you want to check for that, right? So, and these are the rules. There are only 3 rules, which is kind of nice. It's not complicated. So this basically checks that there's a path between any 2 nodes, right? And roughly the way to read this is like path xy is valid if link xy is true, right? That's one way to do it. Path xy is also valid if there's a link between x to z and there's a path from z to y. So you can see we've added a node in the middle of x and y. So this is recursive, right? Path xy is represented twice here, and in the final case here. So it can always go back up here to find a link, or it can go down to the second case to find another link to a node which has a path. So any sequence of links is valid from I to any of the models. So a path from I to C and then C to M1 is considered correct by this rule, right? But that's not enough, because we want to actually, this covers both the first and second rules, right? But those two are not enough because it doesn't describe direct links, right? So we could say that there's a kind of indirect, it would indirectly respect what the user asked for, even if that model didn't actually see what the user asked for. But we can't really trust that, which is why we now add the third rule, which fails specifically. It fails if there's no direct link between this input node, and any decision node. So, and this is what that looks like, right? So it says direct link is valid if there's a link from I to D, where D is a decision node, right? Then this rule says it's something like there are no valid rules, or there are no valid situations where you have a decision and there's no direct link between I and that decision, right? Between the user's question and that decision node. And then another one is there are no rules which are valid for which there's a decision node and there's no direct link between the context and that decision node, right? So this covers CM1. This final one covers CM1, and then this second last one covers IM1, making sure that there's always a direct link between IM1 and CM1. So that's that. And then these final lines are to show the valid situations. So in answer set programming, these are called stable models. So we're saying direct link has stable models if there's a link between I and that decision node. And there are no stable models if there's no decision, if there's any decision where there's no direct link between I and that decision. And there are no stable models for decision where there's no direct link between C and that decision. So these three rules plus the method of encoding these graphs are basically what turns the intuitive arguments I'm giving into a system that can now be implemented as an API or something, where someone can draw the diagrams, and then you have a system automatically checking, does the diagram contain a system that would, does the diagram describe a system that a user would actually want to implement? And this is the claim I'm making, that the systems that you don't implement are the ones where you verified that the user's question is represented by every single model that is being applied in the chain. There should be no gaps, because if there's even one gap, then it means that that model it's only relying on maybe one thing, maybe the context, right, to answer the question. So if the context is wrong, or if the context doesn't really represent whatever the user needed, then it will generate something, and then that whatever it generates will enter the flow. It will enter the data flow, and then the user will be deceived, or they'll get an answer that they don't like, and that's it. So that basically covers the method of describing the systems, the way of checking if the data flow is correct, at least in the diagram that describes the system, and then the way of arguing for one type of diagram versus another, and then a way of automatically checking that the diagram actually contains the right paths, the right data flow is described in the diagram. So that covers the paper itself. So if you have more questions, actually, there's if you want to try this yourself, I have two more diagrams that describe the more complex. I have two more programs, answer set programs that describe the two of the more complex diagrams in this paper. So you can pause for questions. If you want, you can describe these two diagrams, and then actually go to the programs themselves and then walk through them, so you can see what a more complex case looks like. Are there any questions? All right.
Maybe this is just an aside. Is it possible to? Because I noticed that generating the CIDs, you need to, it's like separate from your code itself. But is that way they could be embedded within a code, whether it's like using some directives or maybe like attributes, whichever the language is, the programming language the person is using.
Yeah, so if you got a link to the paper, inside that link there's a notebook, the link to a Colab. I'm going to change the screen share to the Colab.
Okay.
And then we can actually see what that looks like, because the CID is actually complete. Like this code, when it runs, it generates this diagram, right? So unless I'm getting the question wrong, like we have a way to generate it at least here.
My question was like, we are doing it like separate from your actual system. So I was thinking that, is there a way this could be generated from the actual system?
Yes. Actually, yeah, that's
Okay.
a really good question that follows into the direction of the paper, the future direction of the paper, basically.
Okay. I see.
Right. So this library that I'm showing here, ICE, is you can use it to generate these kinds of systems. Basically, the concrete examples I was talking about are all like implemented here, and this image is an example of something that looks like one of these CIDs, but just looks different based on what the designers of the system are doing, right? So you can think of this process is called amplification, by the way, right? Where we are asking one question and then having the system ask sub questions and then aggregate the sub questions into an answer that the user gets to see, right? So each of these steps, so we have one model that's doing this. It's being asked the question. Get subs is the system that generates sub questions, right? So it asks each of these sub questions: what is creating, what is cognition, how does creating affect cognition, and so on. And then there's a third step where these blue fields here, they answer the sub questions, right? So those are different models that do that. And then finally, the answer. These chains here, 1, 2, 3, 4, 5, these sub questions, or rather the answers to them they all get aggregated in the final answer that the user gets to see, right? So this is called a trace, right? And this is basically where the program trace part of the paper's title comes from, right? So use ICE to generate a program trace, and then you can generate now the diagram itself from that program trace. So the next steps are to do that, right? To now actually implement systems where like they hook into the tracing process, and then at each step they add these nodes. They're saying there's C that was found, and then it's linked to M1. There's I, it goes to C, and so on. So that's actually part of the intention that's, to do that in the future, in future work, to take to hook. Basically, it's like you can add maybe like adding a decorator to the language model program itself that says at trace, and then or at generate diagram or something like that, or generate seed or something, and then when you do that, at that point in time, it generates the seed for that question. It makes sense to do it like that, because just doing it just by thinking about it is kind of difficult. It takes basically it takes having read and understood and thought through, discussed it with more than one person to actually know for sure that you've gotten the data flow right, and that understanding each step is what you think it is. So yeah, for sure it would make much more sense if you could automate the generation of the diagrams, so that yeah, at least for practice purposes, so you can at least see the seeds that will be generated from a system that someone has built off the shelf. And later on, the plan is to like have like an even more general API that goes beyond systems that are built in ICE. So if anyone here is familiar with LangChain or Llama Index or any of these other libraries, then each of those have their own kind of program trace thing. Like they're all written in Python, and this is like a Python program calling another Python program. So you can definitely do that. This is like meta programming in Python that lets you hook into the function, find out which function called it, and then and so on. So that process is it's designed pretty well in this library. And they just like if you basically transfer this methodology to these other libraries, then it would help those other kinds of systems have a system that does this. Otherwise, only the people who understand seeds and can read them and can like generate them by thinking about stuff will be able to contribute like this. But in this other way, there's at least an automated API that does it. That's a really good question.
Thanks so much for that.
Yeah. So one of the things I didn't talk about is the basically everything that discusses model internals, right? Because when part of my rationale for coming up with all of this was we have an API like this, right? We have a place where you can see the user's question, the context, the model answer, and the output. Or if you go to one of the like more involved examples, like this one, for example. So if you have all of these steps, then this is actually an API, right? So you can think of a JSON object where one of the keys is the question, the answer from model 1, the answer from model 2, and the answer from model 3. So if we knew something about how the models internally work, right? So this is a large language model. It's horribly complex. There's like billions and billions of weights, and somewhere in there is a reason why a particular answer was generated, right? So there's ways to add that knowledge, right? Can we bring some of that internal knowledge about how the system works to the surface while looking at these graphs? And that's like that's even more feature work. This is like deep into the field of mechanistic interpretability, where we're trying to reverse engineer the neural network that's doing the answering. So if you reverse engineer the neural network and find these numbers or some of these weights that describe something like this answer that is generated by one of these sub-agents is truthful given the context and the question. Right? If you can get some numerical way of describing the situation like that, then this diagram stops being just a diagram and becomes a causal model, because the process by which M1 generates an answer and then M1's answer causes M3's answer to be correct or wrong, right? Like these diagrams demonstrate this path, but if we had some numerical method of determining this, then this becomes a model, like a causal model of the entire system's possible truthfulness, which is really interesting because we do not have such things yet in the science of AI, in the science of language models. So this is one of the things that is like one of the important parts of the future work in this at least in this direction. There are probably other groups doing something similar, but I'm not sure how many others are actually going in this particular direction. So this to me is like unique, and this is one of the things that I'm actually following up on at the moment to find out without all of this graph stuff. If you look at just one of the models and you look at it answering a question, can you find out what numerical way, like if you use statistics or if you use some of the linear algebra methods that have been developed to actually dig deeper into the model and actually try and extract weights that represent something about whether the answer is true or false, then we can extend those methods to this case, because this is just the base case extended with multiple calls. It's just compositional. but it's the best system because this is one model being interacted with, right? So you can think of this as GPT-3 or GPT-4 or BARD or something in the background. So the idea is like with now more knowledge into how these systems are working, we can figure out how to predict at least from a single answer whether we, or rather at least from a single interaction, whether we should trust that model's output. Maybe even without reading the whole trace, without reading the whole question and answer and so on. But that's like, that's a horribly complex problem. We'll surely make like 10% of progress in the next 6 months or something. So just look out for that. That's kind of where one of the places where this is going. So I discussed this simple, at least this rule, and what I want to show is that basically, regardless of the kind of diagram you have, right? Doesn't matter if you have 20 nodes or whatever. These 3 rules can help you determine whether, at least according to the rules, you should accept or reject the design of a system. So that's where we'll go next. So this Git repo, it's in the paper. So at the very bottom of the paper, you'll see it. It's just 2 more examples of the same thing. So this is the example in the README is what I showed in the first diagram, what I was just describing right now, where you have the links, the node types, and then the 3 rules, right? And then if you want to learn how at least the verification process works, I would recommend you install a library called Klingo. It's you can find it on Conda. So this is let me share the link to that. I'll just show it here in the talk, so you can actually get a chance to see it. So it's not complex to install. It should be something like Conda. Yeah. Anyway, this is the library itself. It's so if you want to try it out, please try it. The idea is that this diagram is satisfiable, as you can see here, and this is basically what the process looks like. Right? It looks for stable models. By stable models, it means that it can enumerate every thing that is valid about that rule, right? So if you see here, check, we're asking the system to show the stable models for check. Check has this /1 because it only has 1 parameter. And then direct link /2 because it has 2 parameters. So this is what we're saying. We want to show the stable models of check and the stable models of direct link. We say stable model check has stable models for M1 because there's a path from I to M1, even if it's not direct. That's all it checks for. And then direct link has stable models for C and M1 because there's a direct link between C and M1. Right? If you look at the seed here, there's a direct link. And then it has stable models for direct links IM1 because there's a link here, link IM1, and also in the CID IM1. So that's what they usually do. Systems like this, if they're stable models, it will list all of them, and then it says that they are satisfiable or unsatisfiable. But if they're not satisfiable, it does not list any of them, and that's what we'll see next. So this is this is one of the 7 agent systems. So let me go back to the diagram so you can see it. It's more complex than the others. It also is one of the systems that's in production. So that's why basically I had to include it. But I want to go from visual inspection to looking at the verifier that would fail for it. So we'll walk through the code in the verifier, but this is for the benefit of visually inspecting it. So here we have a node I, context C. Only M1 and M7 have access to the user's question, right? M2, M3, M4, M5, and M6 do not see it. You can see that there's no arrow, right? So the claim is this should not be the case, right? There should not be a design where like the user's question is not visible to these mini models. Not even one of them, right? So and this is what we go for here. So if you take this diagram, rather if you take this code and run it in Klingo, it will show that it is not satisfiable because this rule, this direct link ID, is not satisfied by most of the calls here, right? You can only see two of them here, IM1 and IM7, right? There's nothing from I to any of the other models anywhere here, if you look. So if you run this will be unsatisfiable. That's basically what the encoding of the rules should help with, right? So if you have a description of the graph, then we have a way to run a program on that description to say, okay, we can't accept this. This is not the diagram we're going to go for, at least for implementation. This second one is a different one, slightly different. Let me go back to the code, or the paper rather, and show the second one. This is 7PV2. Right? What I was showing before was PV1. PV2 is, if you look at the I node, there's an arrow from I, M1, M2, M3, M4, M5, M6, and M7. So that context is very important. So because of that, we can claim that this model is one which is satisfiable. And in fact, if you run this code, then it will be determined to be satisfiable. Why? Because it satisfies these three rules. So the thing in the paper that is, I guess, that completes the whole idea is we've gone from descriptions of data flow and then intuitive reasons why we want certain kinds of data flow over others. And then we've encoded the intuitive arguments into a program that we can run that should do this automatically. So to me, this looks like designing like a compiler for a programming language. It's like, so we, as a programming language designer or developer, someone has all of these rules that they want the programming language to follow. But those rules don't matter until they've actually written those rules down into their parser or their compiler itself. And so this is kind of the same thing. So we want, or even like to check that a program is correct or wrong, that the syntax is correct or wrong. So this is kind of the idea we're trying to go. If we design systems based on intuitive rules, that's, as engineers, that's what we do typically. Like we have all of these rules we can argue for and against and so on. But then once we encode those rules into a test, right, like writing a unit test, then our work is much easier, right? Because we can run the unit test many times on many different things. So it should become easier to design systems that now coordinate multiple agents in this way. So this is what I hope the paper basically contributes to, making it easier and possible to communicate the flaws, but also making it easier and possible to verify that a design actually is consistent with the rules that you want it to follow, at least as far as data flow is concerned. And that's it. I think that's we've gone quite over time, but this covers everything in the paper. So if you want, you can cover a bunch more, but I think we can pause here and then answer any questions that someone might have. So are there any questions?
None from me.
Right. So so if you want to ask any more at some point, you can just reach out. The paper, this paper goes through many levels of description of things. So if you want concrete examples, I would recommend that you go through this document, this online book, primer.quat.org. So this is how to write compositional language model programs. It basically goes through these steps, right? So we have a data source, then you ask a question, and then there are all of these sub questions that can be done, all the subtasks that can be accomplished, and then finally the answer comes back to the user. So this is for me like the kind of like the gold standard for learning about this stuff. There's many tutorials online and so on, but if you want a really good introduction to this kind of thinking, this is the book to go through. It has a lot of very interesting content. I will share the link to this to Nanda, and then you'll be able to recommend that. Daniel, you have a question?
Yeah, hi. Sorry, I came in a bit late, but I had a question. So the description that you've given, does it apply to models that are already there, or we have to build the models with the algorithm in mind so that we can get we can do the traces?
It can apply to both, either type, because the way, if I go through the way I wrote the paper, so I had my initial idea was to explain this type of diagram where it's just one model, right? And this I had an example of this because I'd already implemented it, right? And if I understand your question correctly, do you mean this as the model or the entire system? Because this as when using this as a model, this you don't have to have pre-trained this yourself. You can be making API calls to OpenAI API, and it would still be valid because you're relying on the model's question answering capability to perform some task on some data that you have access to, right? So if it's like Azure, OpenAI, or whatever, that's fine. You can also train your own model to do the background of this stuff, but it's not at the point when this actually becomes important. This becomes important at inference time, right? Like when you're actually using the model to do something beyond training it the first time. So you're using capabilities that already exist, hopefully.
Okay, thank you.
Yeah, and then so actually to continue the description, like I took the way I wrote the paper was that I started with this example, and then I went all the way to these like complex examples because some of them were in production. I had this in production, and then I had thought about implementing something like this, but I had reasons why I did not want to implement it. Like I did not want the data flow to be correct, but I did not know why. But then the diagrams helped me explain why I wanted one design over another one. And then these other examples came because I needed simpler examples to walk through each step with fewer models so that it's simpler to walk through the data flow with like when it's a few arrows only. So if you read the paper, I hope it walks through the whole thing in kind of a step-by-step way. Certainly the algorithm at the end makes the arguments more concrete. Like it actually makes it such that it's less necessary to rely on intuition to make a judgment about whether a diagram is correct or wrong. You can just run the algorithm on it after encoding the nodes properly. So that's I think what the algorithm contributes. It's just an automated way of doing something that you'd be doing by intuition.
Oh, okay, thank you.
Thanks so much. I guess there's no more questions. But Brian, this really impressive work. I think I would love to have you back again. I'm sure you have so many other either because here we present papers that either you've read or you've written. So this is the very first paper that not wrong actually, like that someone has come. Then the actual the author has come to present. So is an inaugural thing for us. So we thank you so much for offering actually on last minute to come and present. And then just a call out to folks here, if you have any paper that you've been reading recently or that you love, we still have empty slots for the coming months, October and November. So please let me know. You can just reach out to me either on my email or on LinkedIn, on our LinkedIn group. Yeah, I don't know if there's any other comment or anything for Brian before maybe bring it to a close. Or maybe lastly, I will share the links that so I've just noticed that Teams does not allow people who are outside the org to chat, to send the chat. So I will see what to do. Actually, we need to maybe we'll change these settings for this meeting to make it a little bit easier for people who are external. And also, I'll share the links. We upload our recordings to YouTube. So when I upload in the description, I'll put all the links that Brian has shared here and those that you send on email.
Yeah, totally. I'll share all of the links to you and then facilitate that. So yeah, thank you all for coming to the talk. I'm really happy to be able to talk about this work to more and more groups, just to get feedback on what things I might need to change, and so on. So thank you. This has been really, really, really helpful, and I'm really glad to spread this work. So thank you.
Yeah, thank you too. All right, folks, thanks so much for coming. Have a nice week ahead of you, and I'll see you next month.
Thank you. Bye.
Thanks. Bye.
Bye.